Hello, everybody. Good evening.
Hello.
Okay, so we're going to jump right into this. A few people still joining us here, but we started last Thursday by talking about Mohr circle and how we can use Mohr circle to graphically illustrate the rotation of principal axes so that we can get the normal stress and the shearing stress at any internal angle that we wish. So we talked about the theory of Mohr circle and the procedure of Mohr circle. We're going to start tonight with example number 1, uh, and we're going to draw a Mohr circle. Before we get started, does anybody have any questions they'd like to ask for me? Okie doke. All right, so this is our first example where we have an element. I think these are the same stresses as we've been looking at, but we have in the sigma x direction, 5 ksi in tension. Sigma y direction, we have 3 ksi in tension, and we have 8 ksi for our shearing stress.
Professor,
Yes.
I actually did have a question. Could I ask it right now, or should I just wait now?
No. Now's a good time while everybody's still kind of dinging in.
Well, it was just the circle, the Mohr circle. You said the angle, 2 times the angle.
Yes.
So like 90, like A and F are 90 away, or 180 away.
Okay.
I was rewatching the lecture today. I was a bit confused on that part.
Yeah, that can be a bit confusing. So E and F, or A and H, or B and D, anything that is opposite is theta is equal to 90 degrees. So on the circle, you draw it at 2 times theta. So on the circle, it's going to be 180 degrees. So this angle here, see how it's labeled as 90?
Yes.
Okay, so theta is equal to 90 between A and H, but you draw it at 180 on the circle. So whatever it really is, it's twice that when you draw it.
Okay.
Okay. Um, let's go through the example and hopefully that will clarify it a little bit more for you.
Yeah. Thank you.
Okay. All right. So what we would like to do is draw a Mohr circle, and then we want to find sigma x prime and tau x prime y prime for a theta equal to minus 40 degrees. So we're going to start by finding sigma average. Sigma average is defined as sigma x plus sigma y over 2. So I plug in my 5 ksi, my 3 ksi over 2 is equal to 4 ksi. And my radius of the circle is the square root of the sum of the squares. So we have sigma x minus sigma y over 2 squared plus tau xy squared. And I can plug in those values, 5 minus 3, 8 ksi squared, and the square root of the squares is 8.062 ksi. That's the radius of our circle. So we start by drawing the positive coordinate system. To the right is positive sigma, down is positive tau. And this might be the tricky part, but if you draw it like this, then everything else fits in. We plot the center of our circle, point C, on the sigma axis at the average, which was 4 ksi. So on here, I measure over 4 ksi. If you're using like graph paper, then it's just real easy to just go 4 units over, and you can do it that way. When I draw it in CAD, then I'll say every inch is equal to 1 KSI, something like that, and I'll draw it to scale. So however you draw it, you go 4 units over, that's 4 KSI, that's the center of your circle. Then from there, you find your point A, your reference point, and point A is sigma x over, sigma x was 5 KSI, positive because it's in tension, and you go down 8 KSI for your shear stress, again, positive because it was a positive shear stress. So 5 over, 8 down, and you mark your point A. Then you draw your reference line from C to A, and that reference line again represents an angle theta equal to 0 degrees. Reference line is orientated at theta equal to 0 degrees. And then we draw our circle. So the circle, there's a center, there's a radius point, and you just draw a round circle from there. Again, in CAD, super simple. You just tell CAD, center and radius, and it'll draw that automatically. Any questions so far?
Yes, can you go back like a few slides? Right there, thank you.
Are we good?
Yeah, thank you.
Okay. So the radius of the circle, as I mentioned, is 8.062 KSI. So then we can find at our points. At A is our reference point, B, C is the center, D, E, and F. And each one of these points was found because they're on the perimeter of the circle, right? So B is going to be 4 KSI was the average distance to C plus the radius of 8.062. D was the average of 4 minus the radius of 8.062. F is equal to the average, there's 4, and then you go down, it's up, but it's negative, so you go negative 8.062, and E is also 4 over, and you go down, which is positive 8.062. Okay, so pretty straightforward on how to find points B, D, E, and F. Any questions on that? Okay. At point B, no, okay. I basically just said this, but here's how it's written out. Sigma 1 is equal to 4 plus 8.062. Sigma 1, remember, is the principal stress. So this is the maximum normal stress, 12.062. Point D is sigma 2. Sigma 2 is the minimum principal stress. And as you can see, that's going to be the furthest extent to the left of any point on the circle, minus 4.062. Point E, tau x prime y prime is 8.062. That's the positive one here. And at point F, tau x prime y prime is minus 8.062. That's the negative one up here. So these represent the extremes of the maximums and minimums for normal stress and shear stress. If I wanted to find sigma y, then sigma y is going to be 90 degrees away from sigma x. This was point A. Point A represents sigma x. So again, 90 degrees away is 180 degrees on the circle. And so what I did was I drew a straight line. This is my reference line. I continued that line until it intersected with the perimeter of the circle. And then I measured this, and it measured out to be 3 and minus 8. It's also, it's 3 and minus 8 because that was the original problem statement that sigma y was 3 KSI positive in tension. "90-degree transformation angle is plotted at 2 theta or 180 degrees on Moore's circle." So again, there's the question. We know X and Y are 90 apart, so we draw it on our circle at 2 times 90 or 180. So this is clearly 180 in the circle. All right, so now what we want to do is we want to find sigma x prime, tau x prime, y prime at minus 40 degrees. So this is my reference line. This is where theta is equal to 0. So minus 40 degrees is going to be, well, first of all, minus is going to be clockwise. So I go in a clockwise direction. I go in a clockwise direction. And if I'm looking for minus 40 degrees, then I draw it twice that. Everything on the circle is 2 times what you're really looking for. So minus 40 degrees is drawn at minus 80 degrees. That's why this, you can see this is almost 90 degrees to this. This is 80 degrees on the circle. And this point G is what I'm looking for. So sigma x prime, tau x prime, y prime at this point here at minus 40 degrees, that's what I'm looking for. We could run this through our equations like we did in the very beginning to get these values, but I want to show you how you can get these values from trigonometry or geometry on Moore's circle. So we're going to draw the point at minus 40, which is 2 theta or minus 80 on the circle. We cannot solve for point G directly, graphically on the circle, so we're going to break the angle into parts. Reason that we can't solve it directly is I don't know where this reference angle really is with regards to the circle. How many degrees away is A from E? I don't know that yet. So we need to get some triangles based in here, and then we can figure out where G is. Okay, so we start by finding the angle alpha from point A to point E. This is my reference point, and this is point E. I know my reference point is 5 and 8 from the problem statement, and I know that point E is 4 and 8.062. We solve for these numbers. So we can say that point A, the distance horizontally is 5 KSI minus 4 KSI. So this horizontal distance is 1 KSI. And we know that point A is 8 KSI vertically. So the vertical distance is 8 and the horizontal distance is 1. So I can take alpha as an angle is the inverse of 1 over 8 or 7 1/8 degrees. Okay, so everybody following what I'm doing here?
Quick question.
Yeah.
So for the tau values, why are they 2 different values if they're both the radius, or are they just like so close that it doesn't really matter?
You're saying this guy and this guy.
Yes.
No, they're very different. Tau is the distance from the green line to the point. And A is farther up than E because it's coming up on the circle. E is at the quadrant or the, the minus 270 point. Am I answering your question or are you asking why this one's 8?
No, that makes sense. Thank you.
Okay. Okay, so what we did is we're drawing, actually I can draw it in there if that's a bit confusing. Now watch I draw it in there and then this is the next slide. But horizontally, this is 1 KSI. Vertically, this is 8 KSI. And so see how this forms that triangle? So I have opposite over adjacent is equal to the angle of the triangle. So that's how I got inverse tangent. 1 over 8 is equal to 7 1/8 inch, or 8. 7 1/8 degrees. So that gives me alpha.
I have a question, Professor.
Sure. Yeah.
Isn't it negative 7.125.
Yes. Yeah, I'm not saying that. Okay, E is a negative 7.125 from A. That's not what I'm saying just yet. I'm just saying that the angle between the two of them
Oh,
is
okay.
7 degrees.
Okay, that makes sense.
Okay.
Excuse me, Professor.
Yeah.
So as you double the angle, like, do you need to double this one or you have to keep it like that?
No, you keep it like that.
Okay.
This one's because I got this angle from the geometry of the circle. That's a very good question, but this is from the geometry of the circle. I drew this all absolutely to scale. So that distance is 1. This distance is 8. So the inverse tangent of 1 over 8 is 7.125 degrees. If I measure this in CAD, that is 7.125 degrees. So on the circle, it is 7.125 degrees. Now, what you're asking, and the question just before you was asking, theta on this would only be 3.5 degrees. So theta would be 3.5 degrees, but on the circle, it is 7 degrees. Okay, so now what we're going to look for is psi. I want to find psi because once I have psi, then that gives me down and over from this horizontal axis. So psi is found by looking at the total geometry. The total geometry is going to be 90 degrees from E to D is 90 degrees plus 7.125 degrees minus my 2 times the 40 degrees, because the theta was 40, so on the circle it's 80. And what I'm left with is 17.125 degrees. So this angle here, what you're left with is 17 and an eighth degrees. Like so. So now that I know this, now we can find sigma x prime and tau prime y prime. And sigma is equal to 4 KSI minus, okay, yeah, that's what I did. Okay, so cosine of 17, you know the radius is 8.062. The radius is always 8.062 anywhere on the circle. So the radius is the hypotenuse, cosine is the adjacent, and then the total distance, you have to subtract the 4 KSI from it because you go over 4 and then back out. So what we're left with is minus 3.705 KSI, which is actually this distance right there from the 0 line to G is minus 3.705 KSI. And likewise, tau x prime y prime is the sine of, and I don't need to subtract anything out because I'm going right from the horizontal axis where tau is equal to 0. So it's 0 plus the sine of 17 and an eighth degrees times 8.062 KSI gives me 2.374 KSI. That's the vertical distance here. It's going down, so this is positive, and it's to the left of the vertical axis, so this is negative. And that's how we found point G. Like I said, we could have used the equations that we learned at the beginning of stress transformations, but this reinforces it by showing the geometry on Moore's circle. Any questions at this point?
Professor?
Yeah.
Can we go back to where you plotted the negative 40 degrees? How did you do that again? Like you said, it went from the left and you went to 80 degrees or negative 80 degrees or something like that.
Okay. All right. Well, hopefully we can do this. From E to D is 90. From here to here is 90, right?
Yeah.
Okay, so this is 90, plus we know this is 7. So that's 90 plus 7. But then how far is it from A to G? What's that angle from A to G?
Is that the 17?
From A to G is the problem statement, 40 degrees.
Oh,
But on the circle, that's minus 80 degrees. Equals, okay? So I started here and I went here, then here, and then back to here. And what I'm left with is psi, 17 degrees.
okay.
Okay?
Yeah, I think that makes sense.
Professor, so you know you did something wrong if your sigma and tau is outside the circle, right?
Outside the circle. Well, yeah, I guess so. The point is always on the circle.
Yeah.
You-
Okay.
You can't be solving for a point out here, and you're never solving for a point in here. It's always somewhere on the circle. Because remember what we're doing a stress transformation. Stress transformation means that you're going from a reference coordinate system, which is C to A, and you're going to some other coordinate system, which is simply a rotation from 0 to 360 degrees. So you're just rotating from 0 to 360 degrees. Somewhere on the perimeter of the circle is where any point's going to be. So depending on where that point lies, then you can solve the trigonometry to get the coordinates for that point.
Okay. Makes sense. Thank you.
Okay. Okay, we are here and we solve for those two. Okay, so now from Moore's circle, here's our reference point A. That was given to us as 5 and 8 KSI. We found B, D, E, and F by just knowing the geometry here. And then we solve for G, which is 40, theta is minus 40. And we solve for our point on G. Okay, so this is the same points. Now remember we solved all these points. This is the same problem and we solved them using the equation method. So when we solved for minus 90 degrees and we found 3 KSI and minus 8 KSI, this is just a reprint from the first lecture on this subject. So minus 90 means that you go from A minus 180 degrees, and there's your point right there. That's my minus 90 point. And as you can see, it's a positive 3, and the height of this is minus 8. So there's that first point at minus 90. The next point we did was minus 70. Now we're over here. And see how as we're reducing this angle, we're going less away from A. We're actually kind of working our way towards A. And your sigma x prime is now on the negative side. It's to the left of the vertical axis. And it's still above the horizontal axis. So the tau is negative and the sigma is negative at this point. We go to our next point, minus 50 degrees, and we're here. You can see that minus 50 degrees is actually minus 100 degrees on the circle. And here you can see minus 0.4 KSI. So the shearing stress, the distance, the vertical distance is getting very small. At minus 48.56 degrees, remember these are all the same points that we solved for, then our sigma x is at its absolute minimum, minus 4.062, which meets point D, and the shearing stress is at 0 at this point. Minus 40 is here. We just solved for that. Minus 30 is here. Minus 10 is here. And you can see here now our sigma x is on the positive side. So we're over here on the positive side now. And our tau is very positive. It's almost to the maximum. At minus 3.56 degrees, we have our average sigma stress and our maximum shearing stress. So we're now at this point E. At 10 degrees, see, so now I'm now on the positive theta side from my reference A, and my sigma is at 7.6 now, and my tau is at 7.1 now. So down 7.1 over 7.6. 30 degrees, I'm now at a sigma of 11 KSI, tau is 3 KSI. I get to point B at 41.44. My maximum sigma, my 0 shearing stress. 50 degrees, 70 degrees. So now my sigma x is getting smaller, but my tau is getting more and more negative as it's going towards its minimum value. 86.44, I'm at my minimum shearing stress, my average sigma stress, and back to 90. Okay, so we did a lot of these using the equations. Now we've worked through them on the circle. And hopefully this demonstration shows you, as you go through a circle, how these stresses change and go, again, they oscillate between 0 or a minimum to 0 to a maximum to 0 back to the minimum. Okay, any questions on this? This is the last slide of this lecture. No questions?
So if we were to get like a problem like this on like an exam or something, would we have to list out all of these angles and their values?
Keep in mind that you should be able to. You should have practiced this. You should be able to answer any one of these questions. Also keep in mind that you're going to have 2 hours on the final exam to do 5 problems. So I cannot write one problem that would take an averagely proficient person an hour and a half to work through, right? So we have what you're expected to know and have practiced, but we also have to keep in mind time constraints.
I have a question, Professor.
Sure.
So over here, it's negative 90 and 90. They both have the same tau values, but
Yes.
it's negative 70 and 70. They're not the same.
Right. That is correct. Because minus 90, remember you go 2 theta on the circle. So minus 90, you go 180 degrees clockwise. If you're positive 90, you go 180 degrees counterclockwise. And 180 degrees from A this way and 180 degrees from A this way gets you to exactly the same spot,
Yes.
right? But not so with 70. Minus 70 gets you over here. Positive 70 gets you over here.
But they also have the same tau values since it's both negative
No,
at the top.
no. Okay, minus 70 is about right here. Yeah, so minus 1.9 to the left, minus 5.5 up, rounding up. But the circle is not centered on this line. So this point does not have the same values as this point.
It's diagonal. Okay, that makes sense. It's
Right.
not tangent to the curve. Okay.
Yeah, it's not symmetrical.
Okay, that makes sense.
Okay. Any other questions? Okay. Slideshow.
So just a clarification, Professor.
Yeah.
So the circle is a little bit tilted with respect to the what do you call it? The tau and the sigma.
Yes.
Okay.
Yeah, it's not symmetrical. And also it depends on where A is, right? If A was more off to the right, then the minus 90 and positive 90 would be more off to the left.
Yeah,
A was
you need
skewed and the whole circle is skewed over by the average of sigma x plus sigma y.
right. Okay, that makes sense.
Okay. All right. Well, tonight's lecture is going to be about strain transformation. I do not expect that we're going to get through this whole lecture in 45 minutes, but we'll see what we can do. So let's see what we can do. So there is a bit of a difference, a fundamental difference between stress transformation and strain transformation. And just a quick refresher, I know you all know this because we're getting towards the end of this semester here, but stress is a force over area. Units of stress are KSI. A strain is a measure of deformation. So a strain is a deformation per length of material. So strain is measured in inches per inch. Stress is measured in KSI. Okay. So if I start with a cube of some element of some material, I pull a little cube of material out of a structural member and I label the axes as shown. So I have my X, my Y, my Z axis. Then if we have plane strain means that you only have stress in the plane of X, Y. We're omitting here stress in the Z. If we apply normal stress only to the normals of the X and Y axes, then we're going to get a deformation. We're going to get a deformation due to the stress in the Y, due to the stress in the X. Sigma or epsilon x is going to be proportional to sigma x. So remember Hooke's law? Remember that strain is equal to stress over Young's modulus, or stress is equal to strain times Young's modulus. So they are proportional to each other. So epsilon x dx is the deformation parallel to the x-axis, and it is proportional to sigma x. Sigma y, likewise, epsilon y is proportional to sigma y. The more you pull on it, the more it's going to strain in the y direction. However, even though in this illustration, sigma z is equal to 0, I have no stress point up and down on this element. But remember Poisson's effect? Poisson's effect is if you stretch something out, the diameter gets smaller. If you compress something, the diameter gets bigger. So even though I'm not putting any stress in the z direction, due to Poisson's effect, sigma z is also proportional to sigma x and sigma y. So in other words, you see this element here? The height of the element, assuming this is tension and this is tension, the height of the element is going to be reduced by a sigma z dz. That's what makes strain transformation more complicated than stress transformation. You do not have a cross-axis effect like that in stresses, but we do in strain. So even though this element is subjected to plane stress, we're only stressing it in the X and Y direction. The state of strain is not plane strain, it is in fact three-dimensional. In the real world, plane strain rarely occurs, but we will examine it for the transformation equations. In other words, in the real world, you could take a plate of material, stretch it this way, stretch it that way, and there's really very difficult to keep it from elongating or shortening in the z direction. You'd really have to have something restraining it to keep it from doing that. So it's not very common in the real world. Last example of this lecture will show this effect. Okay. Working with strain components in a plane, 2D, we want to transform strain from one coordinate system to a rotated coordinate system. So it's going to be similar to what we did in stress. We have an x coordinates and we have a y coordinate. And if this thing is pulled in the x and pulled in the y at the same time, it's going to form this, what is that? A rhomboid or parallelogram, kind of a parallelogram type shape. And it's going to have some shear strains that you notice here. So we're going to start with known strain values for sigma x, sigma y, and gamma. That little kinky thing right there, that's a gamma xy. Remember, gamma is shear strain. So we're going to start with known values for sigma x, sigma y, and gamma xy. So now we're going to rotate our coordinate system to an x prime, y prime coordinate system. Strains in the x, or epsilon x, epsilon y are positive if they are elongated in the x or y direction. So these are shown as positive strains, which would indicate tension. Shear strain, gamma xy, is positive if the angle AOB, I haven't marked A and B yet, but if the angle is less than 90 degrees. Transformation angle is positive if it is counterclockwise, as shown, and negative if it is clockwise. Sign convention follows the same as stress transformations. Okay, so if I start with undeformed lengths of the element from trigonometry, dx is equal to dx prime cosine theta. So this is just equal to cosine theta of this. And what I'm showing here is the blue is the original size without any loads on it of the element. So the element is dx long, dy high, and the hypotenuse I've labeled as dx prime because we've transformed it from the x to the x prime axis. dy similarly is dx prime sine theta, where theta is the angle between x and x prime. Now, if I apply a load to it, if the element is going to elongate in the x direction by an epsilon x dx, okay? So here's dx, the original length, and this horizontal length right here is the elongation due to some load, and that elongation is defined as epsilon x times dx. Remember, the new length is equal to the strain times the original length. Or I'm sorry, the deformation, not the new length. The deformation of an element is equal to the strain times the original length. So the original length is dx. The deformation horizontally is epsilon x dx. If that is so, then in the x prime direction, the element has elongated by epsilon x dx cosine theta. Because in this illustration here, the original deformation is the hypotenuse. So the adjacent is the cosine. due to elongation in the x direction. So this red right here, just kind of have a mental note. This is the component of the strain in the x prime direction due to elongation in the x direction. And what I did is I took that strain and I put it up here. You can see from it's parallel. So this length is equal to this length. So this is just one component of the overall deformation. Now we're going to look at the y direction. So if an element elongates in the y direction by some known value, epsilon y dy, so the strain times the original height is the new height. And just by trigonometry, this is theta when this is theta. Then the red line is what we're after. We're after the component of the deformation parallel to x prime. So then the element elongates along x prime direction by epsilon y dy and then sine theta due to elongation in the y direction. And then I transpose this elongation over here so that you can see how it elongates along x prime. This is component number 2. Then we have a component due to the shear strain. If the element elongates from shear clockwise by angle gamma xy, then the element elongates along the x direction by gamma xy times dy. Remember this, the sine of a small angle is equal to the small angle. So we dropped the sine and just went small angle times the original height. Small angle theory. And so there's a component of this little guy right along there that is oriented in the x prime direction. And that little piece right there is gamma xy dy cosine theta. And I transpose that to over here, and those are your 3 components. So adding the 3 components of deformation, my total deformation in the x prime direction is epsilon x dx cosine theta, epsilon y dy sine theta, gamma xy dy cosine theta. Since epsilon x prime is equal to deformation x prime over dx prime, and dx is equal to dx prime cosine theta, dy is equal to dx prime sine theta, we can substitute and we can plug these guys back into here, and we get epsilon prime x is equal to epsilon x cosine squared theta, epsilon y sine squared theta, gamma xy sine theta cosine theta. So it's very similar in look and feel to the stress transformations, but a little bit different. Somebody just revved up something right outside my window, so sorry about that.
Wait, sorry, can you go back to that equation one last time?
Right there.
Professor?
Yes.
So is that the equation for the total deformation in the x direction?
That is the equation for the total deformation in the x prime direction. And the form of this is going to be very similar to the stress transformation form, where epsilon x, epsilon y, and gamma xy are known values for the problem. You don't solve for those. Those are given to you. And the angle theta at which you want to find the new strain is also given to you. So you really, this is a constant, theta is a constant, 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 constant. So this is not too difficult to just mathematically work through. It's really the concepts that are a little more difficult. Okay, that was delta x prime. Now we're going to be looking for delta y prime. I'm sorry, we're not. We're going to be looking for gamma x prime y prime. We're going to be looking, because remember before we found sigma x prime and tau x prime y prime. Now we're going to be finding delta x prime and gamma x prime y prime, the transformed shear strength. So we're going to start from the small angle theory that alpha is equal to delta y prime, the deformation parallel to y, over dx prime, the new length of the deformed along the dx direction. Delta y prime we get from the three components of sigma x dx, sigma y dy, gamma xy dy. We kind of go through the same routine. It's just that instead of this segment, now I'm looking at that segment that is parallel to the y prime. So if the element elongates in the x direction by sigma x dx, then the element elongates in the y prime direction by delta y prime is sigma or epsilon x dx sine theta. Really all we're doing is just switching from cosine to sine. And this one becomes cosine instead of sine. So delta y prime is epsilon y dy cosine theta. And then the gamma version. Remember we took this little guy right here and put it over here. Well, now we're looking for the parallel to y prime version, which is going to be equal to gamma xy dy sine theta instead of cosine theta due to the shear deformation. So if I add the three components together, I have delta y prime is epsilon x dx sine theta, epsilon y dy cosine theta, gamma xy dy sine theta. We're not there yet, but any questions? Okay. Since alpha is equal to delta y prime over dx prime, then we can substitute alpha is equal to, and let's see, how did I, over dx, that was kind of a leap of faith there. How did I get from dx prime? Oh shoot, I should have done a better job of that. Dx prime, we solved for. Delta y prime is equal to all of that. So alpha is equal to all of that divided by dx prime. Sorry guys, I kind of skipped a step, but I guess taking on faith that substituting this over that is equal to this, which gets us a simplistic. And then finally, we need to find the components of gamma prime. So we rotate gamma prime by the angle beta here. Beta is equal to alpha with substituting theta plus 90 for theta. Okay, let me back up here a second. Where was alpha? Alpha was not that angle. There it is. Okay, so alpha is this angle. And beta is this angle. Okay, okay, so beta is equal to alpha plus 90 degrees. Got it. Okay. So beta is equal to alpha with substitution of theta plus 90 for theta. So beta is equal to minus epsilon x plus epsilon y sine of theta plus 90 cosine theta plus 90 minus gamma xy sine squared theta plus 90. And then of course, theta plus 90s simplify. So then we can simplify to minus epsilon x plus epsilon y cosine theta sine theta minus gamma xy cosine squared theta. So now we have alpha and we have beta. Alpha minus beta represents the shear strain gamma x prime y prime. So alpha minus beta gives us, okay. Therefore, gamma x prime y prime equals minus 2 epsilon x minus epsilon y sine theta cosine theta plus gamma xy cosine squared theta minus sine squared theta using trigonometric, I can't even say that now. See what happens, folks, when you start work at 5:30 in the morning? Can't say those words anymore. Okay, so I think these are our simplified. Yes. Okay, so getting to our end result here, epsilon x prime equals epsilon x plus epsilon y over 2, epsilon x minus epsilon y over 2 cosine 2 theta plus gamma xy over 2 sine 2 theta. Gamma x prime y prime over 2, and this is really interesting how we start representing this angle as gamma x prime y prime over 2. But that is equal to minus epsilon x minus epsilon y over 2 sine 2 theta plus epsilon x y over 2 cosine 2 theta. And lastly, epsilon y prime is epsilon x plus epsilon y over 2 minus epsilon x minus epsilon y over 2 cosine 2 theta minus gamma xy over 2 sine 2 theta.
Sorry, Professor, can you go back real quick, please?
To these three? Yeah.
Thank you.
Okay, so this illustration here, the green is the original element before it was stressed or strained. And then once a stress was applied to it, it strained into this new shape. See how it's stretched in the x prime direction, and it has shrunk in the y prime direction due to Poisson's effect. So this is showing us a positive, because it's stretched, a positive epsilon x prime deformation. This is showing us a positive gamma x prime y prime deformation, where the original angle was 90 and now this included angle is less than 90. Similar to principal stress, we can find principal strains. Tangent of 2 theta p is equal to gamma xy over epsilon x minus epsilon y. And so again, same idea that the angle theta p is the angle in degrees that gets you to the maximum and the minimum normal strains. And the maximum and minimum normal strains are equal to epsilon x plus epsilon y over 2 plus or minus the square root of the sum of the squares. This squares being epsilon x minus epsilon y over 2 squared and gamma xy over 2 squared. At principal strains, the shear strain is equal to 0, just like with stresses. Similar to the maximum shear stress, we can find maximum shear strain. maximum shear strain is equal to tangent to theta s, which is equal to minus epsilon x minus epsilon y over gamma xy. So gamma max over 2 is equal to the square root of the sum of the squares again of epsilon x minus epsilon y over 2 squared and gamma xy over 2 squared. Epsilon average is epsilon x plus epsilon y over 2. Okay. Shoo. Any questions?
Could you go back real quick? Thanks.
Was that enough time or did I go too quick?
That's good. Thank you.
Okay. All right. Example number 1. Find the normal and shear strain on a transformed section rotated 30 degrees positive. So here's my original problem statement. Only instead of KSI now, we've got this mu. And did I put on there somewhere? Mu is microstrain. Thought I had it on here. We'll see if it pops up somewhere. But mu is equal to 1 e to the minus 6 inch per inch. So it's a millionth of an inch over an inch, I believe. Yeah, there we go. Finally. Okay. Yeah, mu is microstrain. So it's 1 times 10 to the minus 6 or 1 e to the minus 6 inch per inch. So 200 mu, right, is equal to, really shouldn't do this in my head, 0.002. Yeah, I think that's right. Oh, just to be sure. 200 e to the minus 6 is 0.0002, 3 zeros. So 2000 mu is 0.002. All right, sorry about that. Okay, so that's what mu is. You'll see that in the problem, so I put it here just so that you wouldn't be surprised by it. It's just in some ways a more handy way instead of writing out a whole bunch of zeros all the time. So epsilon x is equal to 200 mu. That is positive, so that means it is in tension. It's trying to elongate. Epsilon y is minus 300 mu, so that is in compression. And gamma xy is 400 mu, so that's positive shear strain. Okay, so given these values, we can then just plug and chug basically into our equation for epsilon x prime. Again, I prefer to write out the equation as it was presented and put parentheses here. And then if you have a negative strain, put it in the parentheses so that you have 200 plus minus 300, 200 minus minus 300, and it helps to keep all your signs straight. Cosine times 2 theta is 30 degrees. So 30 degrees positive is 30 degrees counterclockwise. And then plus 400 over 2 sine of 2 times 30, we get epsilon x prime is 248 mu. Epsilon y prime, very similar, but it's minus here, 200 minus 300. Cosine 2 times 30 minus 400 over 2 sine of 230, 2 times 30. So epsilon y prime is minus 348 mu. And gamma x prime y prime over 2 is minus 200 minus 300 over 2 sine of 2 theta plus 400 over 2 cosine of 2 theta. And gamma x prime y prime is minus 233 mu. Okay, any questions on example 1? We okay to go to example 2?
Yes.
Example 2. Find the principal strains and the angle of occurrence, or what angle does the principal strain occur at? And this one, we got some slightly different values. I got a positive 250, I got a positive 300, but look at my shear strain. My shear strain is going the opposite direction. So my shear strain is going to be a negative 180. So I got epsilon x is 250, epsilon y is 300, gamma xy is equal to minus 180. And so the equation is tangent to theta p is equal to gamma xy over epsilon x minus epsilon y. I plug in my minus 180 over 250 minus 300 and solve. Actually, that solves at 3.6. So the inverse tangent times 2, 37.2 degrees. My principal strains, epsilon 1 and 2, is equal to this equation. And just plug in the values, plug in chug. I got 250 plus 300 over 2, square root of 250 minus 300 over 2 squared plus minus 180 over 2 squared. I get epsilon 1 is the largest value, is 368 mu. Epsilon 2, you do the negative, and you get a 182 mu. And then the shear, the maximum shear strain occurs at tangent 2 theta s is equal to minus epsilon x over minus epsilon y over gamma xy. So I get a negative 250 minus 300 over minus 180 is minus 0.278. Take the inverse tangent times 2, and I get minus 7.8 degrees. And the maximum gamma is gamma over 2. You can see the equation. I'm getting kind of tired of reading out every word. Anyway, square root of sum of the squares, 250 minus 300 over 2, minus 180 over 2 squared, 93.4 mu is gamma over 2, maximum gamma over 2. Gamma max is 2 times this, so 186.8 mu is the maximum gamma. And the average, epsilon average, is epsilon x plus epsilon y over 2, 275 mu. Okay, any questions on that example?
So gamma is like the shear strain, is that what you said?
Yes, it is.
Okay.
So the shear strain as given by the problem statement here was given as minus 180. See how the arrows are going away from the top right quadrant? That makes it negative. And so, Nicholas, are you still there? I think I lost him
Yeah.
again. Oh, there you are. Okay. So these, if they're going towards this top right quadrant, then it's a positive shear strain. They're going away, so it's a negative shear strain. So that was given. And all we're doing is just transforming this through an angle to get to our maximum, which is here.
Okay. I just wanted to make sure I got the right labeling right, because I didn't know if it was a shear strain or something else. So
Nope, you got it.
thank you.
So, Professor, if there's a x prime and y prime over here, so the theta will just theta plus 90, right? If like it's inverted Like there's an angle.
Well, let me try to explain it this way. We found that the principal angle is 37.2. So if you go here and you rotate, and this becomes your x prime.
Right.
So this is x prime. So if you do that, it's along this coordinate axis, 37.2, that you will have your maximum x prime. And then 90 degrees to that, you'll have your minimum or y prime. So 368 is your maximum and 182 is your minimum. And then the maximum shear stress is at minus 7.8. So if I draw that angle, roughly minus 8 degrees, it is along this coordinate axis that you will experience your maximum shear strain. And you'll find your average normal strain along this angle.
Oh, okay. Yeah, that makes sense.
Okay. And then, of course, the next thing we're going to do is use our Mohr circle. Same principle for Mohr circle. We can do it for strain or we can do it for stress. So really the same procedure. We're going to plot the center of the circle on the, that's not the sigma axis though, that's going to be the epsilon axis. There's a typo right there. That's supposed to be epsilon. At epsilon average is equal to epsilon x plus epsilon y over 2. So there's my epsilon axis. This is my gamma over 2 axis. That's why we're solving for gamma over 2, because the way the circle works, we solve for gamma over 2. So epsilon average gives me the center of my circle. The vertical axis is shear strain, gamma over 2. Horizontal axis is normal strain, epsilon. We can plot our reference point at epsilon x and gamma xy over 2. So there's my reference point A. I go down gamma xy over 2, that's my positive shear strain, and over epsilon x, that is my positive normal strain. That gives me my reference point A at theta equal to 0 degrees. Reference line is oriented at theta equal to 0. Then we can plot the radius and the circle through our points at C and A. And the radius is going to be the square root of epsilon x minus epsilon y over 2 squared plus gamma xy over 2 squared. Then we have our same points, B, D, E, F. And we can find for some arbitrary point G at epsilon x prime, gamma x prime, y prime over 2 at, this is theta, but I drew it as 2 theta. Same idea as before. So using Mohr circle, we can find the maximum normal strain epsilon 1 located at point B. So there you are, there's point B that has the maximum shear strain. Point D is going to have your minimum, not shear strain, I just said that wrong. Point B is going to be your maximum normal strain. Point D is going to be your minimum normal strain. And point E will be your maximum shear strain over 2. Point F will be your minimum shear strain over 2. Really exactly the same concept, same procedure as for plane stress. You just have to remember that instead of tau, you have gamma over 2. Instead of sigma, you have epsilon. Point G represents the transformation from x to x prime. So this represents the X original coordinate axis at 0 degrees, and then this would be a positive rotation to a new axis at X prime. Blue line is reference for X, while the red line is the reference for X prime. Angular distance between is the angle of transformation measured at 2 theta. So theta is the transformation angle, and it's drawn on the circle at 2 theta. If a point A represents the original stress, strain, epsilon x, gamma xy over 2, then point G rotated by 2 theta represents the transformed strain, epsilon x prime, gamma x prime, y prime over 2. Clockwise rotation represents negative theta rotation, while counterclockwise is positive theta rotation. Point H represents epsilon y located 90 degrees from epsilon x, just like before. There's your 90 degrees drawn as 180. Okay, so for this example that we just did a minute ago, we want to draw more circle. I got 250 tension, 300 tension, and negative 180 shear strain. Where are we? 171. We got a couple more minutes. We'll see how far we get. Epsilon x is 250. Epsilon y is 300. Gamma xy is minus 180. Epsilon average. Epsilon x plus epsilon y over 2. 250 plus 300 over 2 is 275 mu. The radius is 250 minus 300 over 2 squared plus minus 180 over 2 squared. Take the square root. That's 93.4 mu. So I can plot the center of my circle at 275 mu from the axis. And I can plot my reference point. This is a little different now. The reference point goes at epsilon x, gamma xy over 2. These two values are given in the problem statement. But here we go positive 250, but we go minus 90. So up is negative. So that puts A in the second quadrant instead of the fourth quadrant. And that becomes our reference point. Reference line is oriented at theta equal to 0 degrees. And we have our radius, so we can plot our circle. Again, the radius is 93.4 mu. And then we can find at point B that epsilon 1 is equal to the 275 is this average to the center, plus the radius gives me 368.4 for point B here. Point D is the 275 minus the 93, gives me 181.6 mu to point D here. Point E is gamma over 2 is equal to 93.4 mu, so that's point E here. And point F is the negative up here. And there are the points on our circle. Let's see, how much farther do we? Oh, okay, that's it. All right, so we're right here. Any questions so far? You got 15 seconds. Just kidding. Yes,
Professor.
please. Yes.
Where did the negative 90 come from?
The negative 93?
No, sorry, when we were plotting it on the circle.
Yes, okay, good question. It came from right here. The original problem statement is that gamma xy is minus 180. So when you go to draw more circle, remember what you're drawing is gamma over 2. So minus 180 over 2 is minus 90.
Okay, thank you.
Okay. And then we got down to, okay, we got those 4 points there. Okay. And then epsilon y on Mohr circle is going to be 90 degrees away from epsilon x, which on the circle is 180 degrees. So a 90-degree transformation angle plotted at 2 theta or 180 on Mohr circle. And I think that's good for tonight. So that's slide 197. Do I have any final questions?
Yeah, so if we want to find the like between A and D, for example, we use the same technique that we used earlier.
Yes, you can. You can use geometry
Yeah,
and trigonometry,
or
or
you can use the formula.
you can use the formula. Yes.
Right. Okay. Thank you.
Any other questions for tonight? Alrighty, we'll pick this up on Thursday. Thank you, everybody. Have a good evening.
Thank you, you too.
Thank you.
Thank you.